In this lesson, we're going to be solving linear systems using Gaussian elimination. This is section 6.1. So in previous lessons, we've solved linear systems of equations by using the substitution method and the elimination method. This is just another strategy for solving a linear system. All right, to use this strategy of Gaussian elimination, we have to first know about what a matrix is. So right here at the top of our paper, we define what a matrix is. It's just a rectangular array of numbers arranged in rows and columns and placed in brackets. And the plural for a matrix is matrices. So let's just define some vocabulary. The numbers inside a matrix are called the elements. The order means that we describe the number of rows, M, and the columns, N, and the order is written as M cross N. Sometimes instead of the word order, you might see the word dimensions, and those are synonymous. Matrices are used to display information, and there are many applications out there where we use matrices described here. And matrices can be used to solve a system of linear equations, and that's what we're going to be doing. The more formal name of using matrices to solve a linear system is Gaussian elimination. All right, we have some examples here. Here's some examples of the order. In this rectangular array of numbers, we see one row, two rows. Rows are the M value. So we have two rows, and then when you look down from left to right, we have two columns. So we would say the order of this matrix is a 2 by 2. Now let's look at this matrix. You can see as you look kind of down this way that we have two rows, hence the number 2. But now we have, when you go from left to right, 3 columns. So this is M and this is N. M and N. So we want to associate the letter M with rows and N with columns. Okay, so what's a square matrix? Well, it's intuitive. It means we have 2 rows and 2 columns, or perhaps 3 rows, 3 columns, etc. All right, what's a row matrix? Well, it only has 1 row. So what would the order be for this matrix? Well, we have 1 row, but we have 2 columns, hence 1 by 2. Another row matrix could be something like this, where there's only 1 element in your matrix. Well, in that case, you only have 1 row and 1 column, hence the order is 1 by 1. And perhaps intuitively, we have a column matrix that only has 1 column. Well, the order for this column matrix would be how many rows? 1, 2, 3 rows, but 1 column. Okay. All right, so now we're going to begin defining different situations that we need to be aware of in order to use matrices to solve a linear system of equations. So we're going to have a lot of background information, and hopefully we can culminate in solving two problems, 2 linear systems of equations by using the Gaussian method. But there has to be some background work first. So that's where we're heading for just quite some time. We need to know all these ideas in order to help us. So hang in there. All right, so one of the things we're going to have to do if we're going to solve a linear systems by using Gaussian, we're going to have to write an augmented matrix. All right, so here we are with an example of a linear system of equations with 3 variables. I see that in number 1. What's the augmented matrix that can come from this linear system? Well, first we have to vertically align the variables, which the x's are lined up, the y's, etc. Okay. If we have any missing variables in any of the equations, we have to fill in a spacer of 0x or 0y or 0z. In this case, all our variables have a coefficient of at least, or anything that's non-zero. All right, so that's the first thing we're going to do is make sure that the matrix is lined up according to the variables. Okay, to write the augmented matrix, we're going to switch to the brackets. The brackets are the symbols that indicate, hey, this is a matrix. Look at this first row in this matrix. Okay, these first 3 numbers correspond to the coefficients of the first equation, where 6 is the constant, and it falls right here. In the second equation in our linear system, we have coefficients of -1, -1, -1, and the constant is 9. So hence we have this row in our matrix. And likewise with the last equation in the system, okay, these values correspond to the coefficients of the variables and 0 being the constant. Sometimes you might see a vertical bar that separates the columns into two groups. Okay, it's missing here, but if I put a vertical bar right here, that would represent where your equal signs are in the linear system. So to the right of the vertical bar, you would have your constants, and to the left of the vertical bar is where you're going to have your coefficients of your variables. It's not necessary to have the vertical bar, but if you see it, just know that it's a way to say, hey, these are coefficients and these are constants. All right, just kind of piggybacking on some previous information. If you were asked what is the order of this matrix, well, we have 1, 2, 3 rows. And how many columns? 1, 2, 3, 4. So the order of this matrix would be 3 by 4. All right, here are two examples right here. So if you want to stop the video and attempt to write the augmented matrix for each of these and then come back and see how you did, that might be a good idea. Okay, I need brackets. First, I inspect my linear system. I only have two variables, x and y. They're lined up, and then I do have constants. So I'm going to start with the first equation, pulling over the coefficients and the constant. So 1, 2, 4. In the second equation, I have coefficients of 1 and -2 with the constant of 1. We're done completing the skill of getting an augmented matrix from this linear system. If you are asked what the order is or dimensions of this matrix, it's 2 rows by 3 columns. Okay, number 3, maybe you noticed that we have 3 variables contained in all 3 equations. We have x, y, and z, but the x's aren't lined up, the y's aren't lined up, nor are the z's. So if you wanted to take a moment and rewrite these equations, notice in the top equation you're missing a z term, so you need to fill in a 0z. In the second equation, you're missing an x term, so we want a 0x, and then we have 1y and 1z equals 3. And down here in the last equation, it's out of order and we're missing a y. So if I rearrange this side of the equation, I would put the -x first. I have no y term, so that's 0y. And I have 1z term, and that's equal to 2. That might be the best thing to do, is to rewrite this matrix so that if your goal is to write an augmented matrix, it makes it easier. I'm running out of a little bit of room, but I'll come down here. So grab the coefficients and the constants. And you're done. That's the augmented matrix for that linear system. The order here is 3 by 4, 3 rows and 4 columns. Okay, 4 and 5 have us go back the other way. They give us a matrix that represents a system of linear equations, and they want us to write the linear system given these augmented matrices. So what I see in example 4 is, if I were to put a vertical bar here, right before the last column, I know these are the constants and these are the coefficients. To the left of this vertical bar, I see 2 columns. That must mean there's 2 variables. So I'll just go ahead and use x and y. Sometimes we use a brace on the left to represent the system. So 3x, 2y equals 4. 2x plus 1y equals 1. Sometimes you don't have a closing brace over here. You can have it. So you can have one on the left, both braces, or you don't have to use any braces at all. So go ahead and try this one and then come back and see how you did. I went ahead and filled in the missing terms. You don't have to. You could have just had 7x plus 4 is equals -13 and not worried about lining it up. It wouldn't have mattered. Either way is acceptable. Just watch out for my math lab and the way they prompt you to represent the answer. Okay. Okay, remember our ultimate goal in this lesson is to learn how to solve a system of equations by using the Gaussian method, but this is all background work that's needed. Okay, so when you look at this back part of the worksheet here, this whole top part right here is defining what it means for a matrix to be in row echelon form. Row echelon form. This is a description of the characteristics of a matrix that's in row echelon form, and then reduced row echelon form is just a matrix that is in row echelon but also exhibits additional characteristics. Okay. You might want to stop and pause and read through all of this and kind of process it. Here are 3 examples where we're going to be asked to determine whether these matrices are in row echelon form, reduced row echelon form, or neither. And to be able to respond to this question right here, for each of these 3 examples, we have to know how a row echelon form matrix is defined, and that's what this information is. All right, if we're going to use Gaussian elimination to solve a linear system, we are going to want to put a matrix in row echelon form if it's not already. So the first thing is a matrix that has any row consisting of entirely zeros, is that row occurring at the bottom of the matrix? So let's just kind of go through and look at these 3 examples. Looking at this example right here, I don't see any row that it consists entirely of zeros. If I did, it would have to be at the bottom of the matrix on the bottom row. Okay, look example 2. I don't see any row that consists entirely of zeros, so we're good so far here. In example 3, there is, again, no row with entirely zeros. So far, all 3 of these examples meet this first description. All right, what's the next thing that has to take place? Well, for each row that does not consist entirely of zeros, the first non-zero entry is 1, called a leading 1. Okay, so let's kind of observe down here. If I'm going to be in row echelon form, any row has to start with the first non-zero entry has to be a 1. So let's look at example 1. Let's just go row by row. So look at row 1, what's on top? What's the first non-zero entry? 1, good. Now scan down to row 2. That's 0. What's the first non-zero entry as you move from left to right? Well, it's 1, so far I'm good. Let's go down to row 3. Okay, when you go from left to right, 0, 0, I'm good. The first non-zero entry in that row has to be 1. So far, example 1 here, okay, is satisfying both these requirements. So let's go to example 2. In example 2, the first non-zero entry in row 1 is 1. Skip down to row 2, 0, but that's a 1, that's good. Skip down to row 3, 0, 0, ignoring those. First non-zero entry is a 1. So far, example 2 also satisfies both these requirements that are up here. Okay, look at example 3. I have a 1 that leads off this row, that's good. But when you come down to row 2, that's a 0, but if I'm going to be in row echelon form, that 2 needs to be a 1, and it's not. So right now, I can say that this example number 3 is not in row echelon form. Well, if this matrix is not in row echelon form, then it definitely can't be in reduced row echelon form. Because reduced row echelon form has to satisfy the row echelon form requirements, and this one doesn't. So this is a matrix, example 3, that's neither in row echelon or reduced row echelon form. That was a lot of information. So if it kind of went past you, you might want to rewind and kind of think about what was said again. Let's go to example 1 and 2 again. So let's go back up here to more requirements for row echelon form. Okay. Now it says the leading 1 in successive rows from top to bottom is farther to the right than the row above it, creating a stair-step pattern to the right with 1s possibly on a diagonal. All right, the leading 1 is farther to the right, okay, than the one that's above it in the preceding row. Stair-step pattern. So let's look at this. I have 1 in the first row here. Okay, and then I have 1 here, and then I have 1 here. That's a stair-step pattern. Let's just say that this one was right underneath this one right here. So let's say I interchange these two. Let's say I put this one here and this 0 here. I don't have a stair-step pattern. So this example 1 would not be in row echelon form. But the way the original problem is written, I do have that stair-step pattern. I don't always have to have a stair-step pattern, meaning this. What if this was a 0 right here, 0, and this was my 1? Notice that I would have along this diagonal 1, 1, 0, which is fine if I have a 0 here, as long as I have a 1 that's right here to the right of this 0. So trying to cover a couple of different examples in this one, but going back to the requirement of row echelon form, this one right here is right now in row echelon form. Is it in reduced row echelon form? I need to read further about that. I'll take care of that in a minute. Let's come over here. Is this matrix at least in row echelon form? Well, here's a 1, here's a 1, and here's a 1. I do have another stair-step pattern. So far I can say example 1 and 2 are both in row echelon form, but are they in reduced row echelon form? So read through the additional requirement to be in what we call reduced row echelon form. It says, every column that has a leading 1 has zeros in every position above and below its leading 1. A little confusing. Let me see if I can kind of explain it through example 1. Okay, to be in reduced row echelon form, let's go row by row. So look at row 1. I have a 1 here. Now look above and below that 1. Well, there's nothing above this 1, but there are numbers below this 1. All the numbers below this 1 must be 0, and they are. Now let's skip down to row 2, and let's find the first 1 in that row. Here's 1. Now look above this 1 and look below this 1. If we have only zeros above and below this 1, then we're in reduced row echelon form. Well, that 2 is not, excuse me, if we have only zeros above and below, I hope I said that, okay, this 1, then we're in reduced row echelon form. This is not a 0, so this is now just in row echelon form. I didn't meet the qualification that I have zeros above and below every 1 that leads off every row for example 1, so I can just say I'm in row echelon form. Let's look at example 2. All right, here's, just go row by row. So here's row 1, look below row 1, yep, all zeros, good. Now let's go down to row 2. The first 1 in that row is here. Look above, look below, all zeros. So far so good. Now jump down to the last row in this matrix. Find the 1, here it is. Look above and possibly below. There's nothing below, so just look above. All zeros. Okay, so we're good to go. This is reduced row echelon. Because we met a further requirement of the elements that are in that matrix. Okay, at this point, you don't have this, but I'm going to show you some additional matrices, and we're going to go through making sure that we understand whether a matrix is in row echelon, reduced row echelon, or neither. So just observe. Maybe stop the video. Look at these these 6 matrices, A through F, and you have an idea if when we come back together, you think these matrices are in row echelon, reduced row, or neither. For me, the first thing I'm going to do is I'm going to look to see if any of these matrices are not in row echelon form. I think that's the first thing to kind of tackle and inspect. So I'm looking for any non-zero entries that are 1s in the rows. So what I mean is, look at example A. This row up here starts with 1, I'm good. Then I have a 0, and then I have a 1 here, that's fine. Third row, 0, 0. The first non-zero should be 1. So far this is in row echelon. Look at example B. We haven't seen this yet, but you might look at the middle row right here and go, wait a minute, that's all zeros. And what was the qualification of a 0 row? It has to be at the bottom. So right now I would say for B, this is not even in row echelon form. So therefore I'm just going to respond that this is going to be neither. Because if this matrix is not in row echelon form, there's no way it can be in reduced row echelon. So far I've got one of the answers already. Okay, looking at matrix C. Let's kind of study each row first. I see a 1 that starts off top row. Second row, first non-zero entry is 1. That's okay that this 1 is slid over. It doesn't have to be right here. It's just the first non-zero entry has to be 1. I'm good so far. Third row, first non-zero entry is 1. Last row, first non-zero entry is 1. So far, this is at least row echelon. Okay, matrix D. I see a row of zeros. It's at the bottom. 1's down the stair step. I'm good here. We'll come back and decide if these row echelon matrices are reduced row. Look at example E. I see a 2 here. That's the first non-zero entry, but it's supposed to be a 1. So I'm going to say that this matrix is neither. All right, look at example F. 0 row, it's at the bottom, good. Top row doesn't start off with a 1, that's okay, but the first non-zero entry is 1 and it's right here, it's okay. Now drop down and let our eyes look at row 2. 0, 0, 1, yep, we're good here. So far, the ones that are remaining, these 4 examples, they're at least in row echelon. Let's go further and see if they're in reduced row echelon. Remember, reduced row echelon means that you look for the ones that lead off each row, and then you look up and down, above and below that one. If you have nothing but zeros above and below those ones, then that's further in reduced row. All right, so example A. Here's my 1. I look down, all zeros. Okay, now I'm going to go to this one. I look up. There's not a 0 there, so this is just row echelon. Okay, skipping down to C. Here's a 1, all zeros below. Skip down to row 2, find your first 1, here it is. Look above, that's not a 0. So this matrix is again just in row echelon form. Look at example D. Here's my first 1 in that row, all zeros. Skip down to row 2, here's your first 1, above and below are all zeros, so far so good. Go down to row 3, here's your first 1, above and below that 1 are zeros, and there's not a 1 in this last row, so this is in reduced row. In our last example, F. This is also in reduced row echelon. Now, this is a lot of background information, and we haven't even gotten to the process of how to solve a system by using Gaussian elimination. But this information all needs to be in place for us to understand. So we still have one more thing to look at before we can put all of these ideas and skills in place to solve a system of linear equations. So hang in there. Okay, we just need this background to help us solve. Okay, now I'm going to go back to these notes. Okay, why do we care about a matrix being in row echelon, and even better yet, reduced row echelon form? Because it helps us solve the system of linear equations. So before I get to the last thing that we need to be aware of, so that we can put all these skills in place to solve, I want to show you why we do this. So for example, if we were to look at number 2 back here, if I had a matrix that represents a system and it is in reduced row echelon form, we can say, oh, all right, I'm going to put my vertical bar here. These are all the coefficients of the variables. in the equation, and this is the constant. If you were to take this augmented matrix right here that's in reduced row echelon form and write a system for it, let's think about what that would look like. Well, 3 columns to the left of the vertical bars means that I probably have 3 variables. X, Y, and Z are common practice to use. So if I were to write the system represented by this matrix, I would have 1x plus 0y plus 0z equals 4. If you slip down to row 2, this is 0x, 1y, 0z's equals 3. Then right here, I would have no x's, no y terms. I would have z equals -2. You're done solving this system if this matrix, augmented matrix, is in reduced row echelon form. I've got my answers. My answer to this system would be 4, 3, -2. If this augmented matrix represented a system. So is it helpful? Yeah, it is to solve a system. But how lucky are we going to be that, you know, our augmented matrix is in this form right here to where we can get right to the answer? I wish we could always be that lucky. Well, sometimes we're going to have to put our matrix in this reduced row echelon form, and more likely row echelon form, to get the system. All right, I want to take a look at example 1 for a minute. What if this represented a system? This matrix is not in reduced row, but it is in row echelon form. We might have to do a little more work than having a matrix in this form. So for example, okay, I'm going to put a vertical bar here. Okay, let's say that this represented the system of 1x, 2y, -z equals 4. The second row would be no x, 1y, no z. That would be y equals 3. Oh, at least I have one of the variables. And the last row would be, I think that was a positive, or was it a negative? Well, I think it's positive. That would be z equals -2. Now, when I write this system of equations right here, I already have y and z. To get x, the only unknown, I would just replace 3 in for y and -2 in for z, and I could solve for x, and I'd be done. So row echelon form is helpful too in solving a system. We might have to just do 1 back substitution or maybe 2. Unlike here, if you have a reduced row echelon form, you can visually see the solution right away. Just wanted you to see where we were going, and especially for the last thing that we need to do, okay, and why we do what we do. All right, so one last thing here for solving systems using Gaussian elimination. And because it does take quite some time right here, I think I'll do this in the next video. I'll do this last thing that we need to be aware of so that we can solve a problem. So I'll pick up here in just a second.